So, you solve it, the easiest way of solving it is to simplify the problem, and it is not an easy problem. So, you pretend that there is no potential, and when there is no potential you can solve it in terms of a base pair, which is e to the ikr and e to the minus ikr. So, any means you can write these in terms of the sine and cosine functions, and then you have an equivalent basis in sine and cosine functions. So, all you need is linearly independent functions. But then when you plug in the potential, and this is a result from standard scattering theory which I will use, the solutions, the radial solutions turn out to be exactly the same as you have if there was no potential, except for the fact that the argument of the radial function is phase shifted. The argument is shifted through a phase. You have got sinusoidal functions, and that is a phase shift that you call as the scattering phase shift, because it is caused or it is brought about due to the interaction with the target potential. So, your reference is having no target, 0 potential. You are interested in what is it that the potential does, and what the potential does is very minimal but very significant. Minimal in the sense that the solutions have got the same form. You get a sinusoidal function in the asymptotic region. As r tends to infinity, you get sinusoidal function. But the argument of the sine function is a phase angle, and that phase angle is shifted because of the potential. That is the scattering phase shift. And that, as I mentioned in the previous class also, you have a 2 delta L phase shift in the scattering. So, now our incoming incident plane wave you can write in terms of the Legendre polynomials, you can write it in terms of the spherical harmonics, but then if you carry out the summations over the m quantum number, it will reduce to this. And here is the important result which I just talked about, that if the potential is 0, the argument of the sinusoidal solution, which is Kr, for every value of L drops by pi by 2 for every subsequent value of the partial waves. You need solutions for all the partial waves. You get the solution only for L equal to 0, which is very easy to get, because you just throw off the term V equal to 0 and you have a very simple differential equation to solve, which is just as simple as that of the simple harmonic oscillator or something like that. You get a sinusoidal function, but which is the phase of the sine function, sine theta, that theta is Kr. It drops by pi by 2 for every value of L. So, if L is equal to 1, it drops by pi by 2. If L is equal to 2, it is 2 pi by 2, which is pi. So, there is a drop through pi by 2 for every additional value of L. And then if the potential is not 0, then there is a further change in the angle which is due to the target. That is the scattering phase shift, and the argument of the sinusoidal function, so the form of the solution remains the same, but there is a phase shift which is the scattering phase shift. And I refer to this as the phenomenological solution. Okay, this is a term which is not always used, but I think it is very useful to use this term. This is not the solution of the differential equation, but it is a phenomenon. It expresses the phenomenon of scattering, that you have got an incident plane wave, it gets scattered out. So, there is an outgoing wave, outgoing because there is a time dependence e to the minus I omega t coming from the stationary state solution. and the 1 over r takes care of the amplitudes, and there is a scattering amplitude which depends on angle. So, it represents the phenomenon, and the actual solution, the form of the solution we get by comparing the solution to the differential equation, which is the Schrodinger equation, with the phenomenological solution, and this comparison requires you to have exactly the same coefficients of the independent basis function. So, if the basis function is e to the ikr and e to the minus ikr, the corresponding coefficients in the two expansions must be exactly the same. So, those are the boundary conditions which help you determine the coefficients, and the solutions for the typical scattering problem are obtained using this. And from this comparison you get the expression for the scattering amplitude. This is normally referred to as the Faxon-Holtzmark equation, I think, for the scattering amplitude. And now we see that the scattering amplitude has got the phase shift twice delta L, twice delta, because there is a delta each way as the wave approaches the target and as it recedes. So, that is where the 2 delta is effectively coming from. And you can write the solutions in terms of a base pair which now inclusive of scattering would be UL minus and UL plus, in which you have an additional phase of 2I delta or 2 delta. So, you can write your scattering solutions in terms of the base pair UL minus and UL plus. The uppercase A is an overall normalization, and now once you get the solution psi, which is this, you can get the probability densities. And if you remember Smith's criterion, he is talking about the excess density. So, you really need the psi star psi, which represents the density. So, psi is the wave function, psi star psi is the probability density. When you integrate this over a volume, you get the probability. So, probability, probability density and probability amplitude are 3 different things. They have different dimensions, and we are now interested in the probability density and use it in Smith's criterion of time delay. So, we are interested in determining what is the excess density in the scattering region. So, if you say that the scattering region is up to R, capital R, whatever be its value, it does not matter. Eventually we are going to let this capital R go to infinity, so that you consider whole space. So, the excess density is the integral of this probability density minus the corresponding probability density when V is 0, and you subtract this from the probability density for V not equal to 0. It is this difference which will give you the excess density, and the net density is the integral of this density. So, d zeta is the volume element r square dr sine theta d theta d phi in spherical polar coordinates, or d omega r square dr d omega. This is the excess that we are interested in. You can get the density for 0 potential. This is when there will be no scattering and therefore no phase shift, delta will be 0, and you can easily get it to be 1 over r square. These are the spherical harmonics, and you have to subtract this from the corresponding density at V not equal to 0. Very simple analysis, but very interesting. So, we have to get this excess density divided by the ingoing flux. We can also divide it by the outgoing flux, because no particles are created or destroyed. So, it is going to be the same. So, it does not matter which one you use. So, let us determine the ingoing or the outgoing flux, it does not matter which one. Either of them will work, because the current density vector is solenoidal, its divergence goes to 0. So, there is no creation or destruction of particles. It is a conservation principle, and we determine the flux for the ingoing waves. So, the ingoing waves are the phi, if you remember. Okay. So, you determine the ingoing flux as the surface integral of the ingoing incident current density vector J. J is the current density vector, and it turns out, using the wave functions that we have written on the previous slides, which are the usual forms of the wave function, this flux is determined, it is equal to the velocity. It also has the normalization constant A star, A and A star, but we have to normalize this, and we can normalize it in many different ways. There is no absolute way of normalizing it, because these are continuum states, they are not really square integrable, but you can normalize them using box normalization or using some other way of normalizing it, and we normalize it to unit incidence flux, so that there is one particle per unit time per cross sectional, per unit cross section in 1 second, or whatever be your unit of time, and that gives the constant A to be 1 over square root of the velocity, and that gives us this density for V equal to 0, which is for free particles, to be 2 over V r square, and then you have got the density of the spherical harmonics. So, we have got this term now, the V equal to 0. We have to ask what is the corresponding density for V not equal to 0. So, this is the question that we now have to get, so that we get the excess density that Smith is talking about in his criterion, and we get it from the Schrodinger equation, which is we separate out the time dependence. So, whenever we talk about the Schrodinger equation, people often write H psi equal to E psi. I always like to remind them that that is not the Schrodinger equation, that is only the Schrodinger equation for the stationary states. And then when you separate out the time dependence, it represents the corresponding differential equation for the space dependent part. And if you take a derivative of this with respect to energy, then you have the equation in the third row, which is very straightforward, as you can see. There is nothing big about this derivative, and that tells you that you can write the wave function psi in terms of h and these derivatives of psi with respect to energy, and you have got now the Hamiltonian operating not on the wave function, but on the derivative of the wave function. Okay, that is the key point here, that is an interesting point. And once you have psi, you can also get psi star by just complex conjugating it, and from this complex conjugation you generate the product, which is the density, which is what you are looking for. Okay. So, you get psi star psi, and then you have the operator H, which has the kinetic energy operator as well as the potential energy operator, but the potential is a real potential. Okay. So, on complex conjugation it is the same, and then there are certain cancellations because it is the same on complex conjugation. So, in your end result you have only the kinetic energy term, okay, the term in the V cancels out, and the kinetic energy term, this is the Laplacian. T is the Laplacian operator. Okay. Momentum is the gradient, kinetic energy is the Laplacian, which is del dot del, and you can write this in terms of the divergence by doing very simple manipulation. If you take the divergence of a product of functions, there are usual relationships in vector calculus that you are familiar with, which you would use to write the density in this term, and its integral over whole space will give you the net probability. But when you take the integral, the volume integral of a divergence, it is completely equivalent to the surface integral of the vector whose divergence you are talking about. What is this? This is the Gauss's divergence theorem, right. So, this is the Gauss's divergence theorem that we are going to make use of. So, you have the divergence of this vector and you take the volume integral of the left hand side and you have a surface integral of the dot product of the vector with an elemental surface vector. The surface element is a vector, in fact it is a pseudo vector, and this is a surface integral over a closed surface which encloses the volume over which the integration is carried out on the left hand side. So, this is the closed surface. On this surface there are these small patches of surface elements, that is ds, which is a pseudo vector, and you carry out the surface integration. We have made use of the Gauss's divergence theorem, and now we make use of the relations that we have introduced earlier and rewrite this in terms of u rather than psi, because psi we write in terms of r and r we write in terms of u, and we have surface integrals which will involve integrations over angles. They will generate some factors like 4 pi and so on. There will be some cancellations, and you are now left with terms over distance, and you have what you are left with is the difference of two terms other than the constants h cross square over 2m. You subtract u star and the second derivative of u with respect to r and e from the first product, which is del u by del e and del u star by del r. You can work this out, it is a good exercise. We can use these recursion relations which I had mentioned earlier, that you can get ul from ul minus 1. These recursion relations are available in any book on quantum mechanics. Landau and Lifshitz is my favorite, and I hope that my book will be your favorite, but it has that relation. But Landau and Lifshitz is simply great. Means I think if you learn from Landau and Lifshitz, you will really understand it. And this integral, if you plug in all these recursion relations and so on, you get this density, you get the integral of the density, and it turns out to be what is given in this equation. The last term is important only for L equal to L greater than 0. For L equal to 0 you do not have that term, but it does not matter, because we will be interested in the asymptotic limit in which capital R goes to infinity and g over r will anyway go to 0. But it is important for us, but not important because eventually it will go to 0. but for L not equal to 0 it is there, and one should keep track of that. So now we have almost everything that we really need for our analysis. So the Smith time delay, which is introduced as the excess number of particles near the scattering center divided by the ingoing flux, the excess flux, the excess number of particles represented by this difference in the densities, we have all the terms, we determine what it is for the 0 potential, we have determined it when the potential is not 0, and we now get the Smith expression for the time delay. The 2r over v cancels, there is one with plus sign and one with minus sign. There is a g over r which does not cancel, but it goes to 0 as r goes to infinity, and now you are left with two terms, which is twice h cross del delta by del E, and then there is a sinusoidal terms which is an oscillatory terms, and these terms cancel each other in wave packets, because at large r, when you have many k's, for small difference they will create oscillations, and a part of what is going up will be cancelled by another part of what is going down. So if there are number of things, oscillations around each other, on the whole everything will be flat. So the oscillatory terms cancel out, and what are you left with? This is beautiful, isn't it? It turns out to be exactly the same as the Eisenberg-Wigner time delay. This is amazing. It has a totally independent origin. We did not start with the wave packets and the time delay in the wave packet due to the interaction and so on. We have a completely independent criterion, but we get a result which is the same. Yes, it is. And this is the Eisenberg-Wigner-Smith time delay, or the EWS time delay. We know the element of the S matrix has this twice delta phase shift. So you can write it as the imaginary part of the logarithm of S, okay. And now we are about to arrive at a very interesting result through very simple steps. Now let us quantize the time delay. Okay, I said that there is an operator for time delay. So let us quantize it. Now what is quantization? What is meant by quantization? And many people think that it is having discrete energies, which is not the case, okay, because you do have continuum energy states in quantum mechanics. And if you ionize the hydrogen atom, give it 13.6 electron volts, but you can give it 13.7 electron volts, you can give it 13.8 electron volts. And what does the electron do? It goes into the continuum with excess energy, but that can be 13.7, 13.73, 13.737, whatever, there is a continuum. And all of those states are eigenstates of exactly the same Hamiltonian of which the bound states are. What is the difference? Only the boundary conditions of the differential equation. The discrete states go to 0 as r goes to infinity, whereas the continuum states are oscillatory. So the boundary conditions are different, and quantization does not mean having discrete states. Discrete states is quantization, but quantization is not discrete states. Quantization is use operators in place of dynamical variables. Instead of q and p, the classical dynamical variables, use the operator for position, which in the position representation is position operator, and the operator for momentum is minus I cross gradient operator. So, using operators in place of the classical dynamical variables is quantization. So, now we are quantizing time delay, which means that we have to write the operator for time delay. So, look at this third row on this slide. You are going from the Eisenberg-Wigner time delay to its quantum nature. Quantization is indicated by the letter Q on this arrow, which means that tau Smith, which is h cross energy derivative of twice delta, you have to write this in terms of an operator. This is quantization, and 2 delta we have written in terms of the imaginary part of the logarithm of s. S is an operator, we know that, and this is your operator for the Eisenberg-Wigner-Smith time delay. It is for the Smith time delay, but it is the same for the Eisenberg-Wigner time delay because they are the same. So, this is quantization, and using simple manipulation you see that this is minus h cross s dagger, and you have the derivative of s, which is s prime. So, this is simple algebra that you can do in a few minutes, and this is important because a very simple differential analysis, you can take the derivative of s dagger s, which gives you the relation s prime dagger prime represents the derivative with respect to E. So, s prime dagger s plus s dagger s prime equal to 0. So, you can write one as the negative of the other, and you use that in the previous relation, and you can write the operator as plus I cross s prime dagger s E, and if you take its adjoint, it is the same. We are done, the class is over. Okay. The time delay operator turns out to be a self-adjoint Hermitian operator, and you need it to be a Hermitian operator if it is to be an observable at all. So, there is no operator for time, but here you have an operator for time delay, which is a Hermitian operator, which is you explicitly see its self-adjoint character. But then we still have to figure out how the solutions of photoionization are related to the solutions of scattering, and that is something we will discuss in tomorrow's first class. So, tomorrow we have 2 lectures. I will discuss the time reversal symmetry. I mentioned that t going to minus t is straightforward in classical physics because classical equations of motion are invariant as t goes to minus t, but in the Schrodinger equation you have the first derivative with respect to time in the Hamiltonian, h cross del psi by del t. So, you do not get a minus sign, you get complex conjugation actually. So, I will discuss that tomorrow. So, as t goes to minus t, there is a complex conjugation that you have to keep track of, and that is important in the interpretation of time reversal symmetry, and this is an operator which turns out to be anti-unitary rather than unitary operators. So, I do not know if you have had a chance to work with anti-unitary operators, but they have properties similar to unitary operators, but I will discuss some of their important properties tomorrow. So, I will discuss the quantum mechanics of anti-unitary operator tomorrow, the time reversal symmetry in particular, and then I will relate the solutions of photoionization to the solutions of scattering, and then argue that if you have a scattering time delay, you can obviously have a photoionization time delay because it is the same quantum mechanics under the time reversal symmetry. So, thank you very much.